In this video, we're going to go over a few examples of rings. So just as a reminder, a ring is a set having two binary operations. And those are addition and multiplication. And those two operations have to satisfy certain properties. It's not enough for there just to be two binary operations, and we call them addition and multiplication. But we'll talk about those other properties as we go through some of the examples. All right, so what I think is the most classic example of a ring is the set of integers. That's a classic case in which we have two binary operations. We can add any two integers. We can multiply any two integers. And furthermore, we can go through and check that all of the properties that we want hold up. So for addition, we know it's associative. We know there's an identity. That identity is 0. And we know that there are inverses. In other words, if x is in z, then what we call negative x is in z. And also, addition is commutative. Remember that addition has to be commutative for us to have a ring. So all of these properties check out. Multiplication, we know that there is a multiplication. Multiplying any two integers gives me an integer. And what else do we need? We need it to be associative. Check. And we know that we have the distributive law. That is, if I have any three integers, x, y, and z, x times the quantity y plus z does equal xy plus xz. And the other way also works, y plus z times x always equals yx plus zx. Furthermore, and these are not required for z to be a group, but I do know that my multiplication is commutative. I'll just put that over here, commutative. That's a check, so this means that we have a commutative ring. And also there is a multiplicative identity. That is also not required, but it's nice to have. So this is an example of a commutative ring with unity. All right, here's another example. The set of real numbers with the operations of addition and multiplication as they're usually defined, that is also a ring. I'm not going to go through and check all the properties one by one again. You've probably known for a very long time that addition of real numbers is associative, that 0x is an identity, that they're inverses, addition is commutative, all of this other stuff is true. And we also know that multiplication is still commutative for real numbers, and we know that there is an identity. That is, 1 is a real number. Okay, so why pose this as a separate example? Well, this has an interesting property that I claim that z doesn't have. That interesting property is, so first of all, this is a ring. It's a commutative ring with unity. And a lot of the time when I write commutative ring with unity, I'll just write commutative ring with and then the symbol 1. But it has another property as well. And every non-zero number, every non-zero element, in other words, every element of the ring that is not the additive identity, has a multiplicative inverse. That is a nice additional property for a ring to have. And if a ring has that property and also has the property that multiplication is commutative, so let's say R is commutative, and every element, every non-zero element has a multiplicative inverse. When that happens, we say R is something called a field, and we're going to spend a lot of time, not so much in this course, but in next semester's course, studying properties of fields. So those are a couple of examples, and the real numbers are one of the nicest examples of rings. It has all of the properties that you like for rings to have. It's commutative, it has unity. Every non-zero number has a multiplicative inverse. Now let's go to the other extreme. So the next example, I guess I wouldn't characterize it as the other extreme. There are some nice things about this ring, but there are also some not so nice things, at least if you like commutativity. So if I write down M 2 by 2 R, this is the set of all 2 by 2 matrices of real numbers. And I claim that this is also a ring. It's a ring because we know how to add matrices. So there is addition. It's associative. There is an identity. This time we have to think a little bit hard about the identity. The identity is this matrix, 0, 0, 0, 0. That acts as an additive identity for all 2 by 2 real matrices. And every matrix has an additive inverse. So notice that these are all for addition. I'm not saying that there are multiplicative inverses. In fact, quite often there are not. And also, addition is commutative. So all the addition properties are in place. Multiplication is a little bit trickier here, but we always can multiply any two 2 by 2 matrices. So we are close. We do have a multiplication operation. It is still associative. We've talked about how matrix multiplication is associative. Distributive law, I believe we have a distributive law. But if you're not sure, you should just check it. I mean, just check that if I take a matrix and multiply it by the sum of any 2 matrices, let's just call these W1, X1, Y1, Z1, and then have another one here, W2, X2, Y2, Z2. If I multiply those, I get the same result as if I do the multiplication separately and then add. Okay, this is more laborious to write down than anything. I'm not going to actually do the multiplication. You can do that on your own. Verify that this works out. But yes, matrix multiplication is distributive over matrix addition. Okay, I'm just going to ask you to trust me on that. All right, but what about other properties? So this satisfies the bare minimum properties for a ring, but what about other stuff? Well, first of all, commutativity is out for multiplication. And just to have one example on the board here, let's take 0, 1, 1, 0 times, let's say 1, 1, 0, 1. If I multiply that way, then I get, and I hope you know how to do matrix multiplication because I'm probably not going to do all the steps except just to show you what I get. But I get 0, 1, 1, and then another 1. But if I multiply the other way, then I get 1, 1, and then 1 and 0. Okay, and those two results are not the same. So that's just one example showing that this particular ring is not commutative. When we say a ring is not commutative, we're referring to the multiplication. Addition always has to be commutative. Do we have unity? Is this a ring with unity? And the answer is actually yes. There is an identity. It is 1, 0, 0, 1, what you recognize as the 2 by 2 identity matrix. So here we have a ring with unity, but that is not commutative. Here's one more example of a ring. Let's take Z mod 10. This is a ring because I can add numbers in Z mod 10, and I can multiply numbers in Z mod 10. The addition has all the usual properties. I'm not going to write them all down again, but it is associative. There's an identity. I will write that down because I kind of want to have this for later. Okay, so addition, it's associative. There's an identity. We call it 0. There are inverses. And just as a reminder, that's like, for example, 3 plus 7 is 0, so 3 and 7 are inverses of each other. You can figure the other examples, and addition's commutative. But what about multiplication? It is associative, it is distributive, and the multiplication operation is even commutative. So what we have here is a commutative ring with unity. Why with unity? Because there is a multiplicative identity. Multiplicative identity is 1 mod 10. So remember, we used to call these like 1 in brackets to represent that this is a congruence class, and we rarely do that anymore. And I'm probably not going to do that here, but you should always remember these are congruence classes. Okay, so we've got a commutative ring with unity. It does have some elements that have multiplicative inverses, but not all of them. Not all of the non-zero ones have multiplicative inverses. So for example, I know that 3 times 7 in Z mod 10 is 1 because 3 times 7 is 21. 21 mod 10 is 1. And 1 is the multiplicative identity. So 3 and 7 are what we call units. More about this later. But a unit is any element of a ring that has a multiplicative inverse. But 2 is not a unit. And for now, we're just going to prove that using good old-fashioned number theory and common sense. Why is 2 not a unit? For 2 to be a unit, we'd need 2 times some element of the ring equal to 1. So 2x equals 1 for some x in Z mod 10. And, well, 2 times anything is going to give me an even number, mod 10, 2, 4, 6, 8, or 0. I'm never going to get 1. This has no solution. So in other words, 2 has no multiplicative inverse. So Z mod 10, while being a very nice commutative ring with unity, is not a field. Because there's this non-zero element here, 2, that has no multiplicative inverse. It's not a unit. And I could say the same for 4, 6, or 8. Okay, but now here, you want to see something really weird? Here's something really weird. We can also take what's called a subring of Z mod 10. So we'll call this example 4.1. Suppose I take Z mod 10 and I extract the following subset, 0, 2, 4, 6, 8. Okay, I always love showing people this example. This is still a ring because it is still closed under addition and closed under multiplication. And you can show that if you have closure under both operations and you still have inverses under addition, which this one does, like the inverse of 2 is 8, the inverse of 4 is 6 under addition. If we have all of that, then we know that this is a subring. It's a subset of Z10 that is a ring in its own right. We can do all the operations we want within this subring. And now you'll notice that we've lost the multiplicative identity. We've lost the number 1. So it looks like, by all accounts, this is going to be a commutative ring without unity. So I'm going to write that down. Commutative ring without unity. But not so fast. I'm just going to ask you to watch as I do the following operations. 6 times 0 is 0. 6 times 2 is 12. Mod 10, that is 2. 6 times 4 is 24. Mod 10, that is 4. 6 times 6 is 36. Mod 10, that is 6. 6 times 8 is 48. Mod 10, that is 8. So 6 times 0 is 0, 6 times 2 is 2, 6 times 4 is 4, 6 times 6 is 6, and 6 times 8 is 8. So 6 is a multiplicative identity for this ring. Weird, right? So depending on who you ask, this subring, the even subset of Z mod 10, it actually is a ring with unity. Now, people will differ on this. Some people will say that for a subring to be a ring with unity, or for it to be considered a subring with unity, technically a subring with unity, it has to have the same multiplicative identity as the parent ring from which it came. I don't know of anyone specifically, any specific textbook that imposes that, but I think I've heard of that before. Really, the case in which the subring has a multiplicative identity but has a different one than before is so rare and so strange that we rarely study it, and we don't really bother too much with having a standard language around that. But I just wanted you to see an example that shows that it is possible to pass to a subring and appear to lose the identity, appear to lose unity, but then have some other element step up and become the multiplicative identity, which this wouldn't have been if we'd been talking about all of Z mod 10. Like 6 times 1 is 6, 6 times 3 is 8. So in that situation, 6 is acting in no way like a multiplicative identity. But if you restrict to the even numbers, it actually does. Kind of weird. Kind of a fun little note on which to end this video.